Yeah, I feel bad. Whatever. I didn't intend anything personal by it. I have to reread what I said and see if I did say anything.
I have to read and see. Oh, yes, I'm recording now. Okay, so my diagram here. Here's my scattering center. And here's my incoming particle, which then scatters away. Okay, I'm just doing that to be complete. Okay, now for the important demarcations. I'm going to start with the easiest one. Which one's the easiest one, Benjamin?
B.
B. So B is the impact parameter, and that is the distance from the line going straight through the center to the line of the incident particle. Then we have the d sigma. D sigma is an area element that it comes into. And finally, D, that's the wrong color. Magenta it is. Now I did the D's instead of sigma and omega, but they relate to the same thing, so it gets us there. So here's my picture showing them. The cross section is, nice choice of colors. Go back to the same one. The cross section is very literally the area in which the incident particle comes to the scattering center. So when I have d sigma, that's some small amount of area that it's coming through. When I have sigma by itself, that's adding it all up. And it tells us the probability of interaction. So that's its usefulness. It tells us the probability of interaction. So an area in which the incident particle comes in, but we have the cross section for something like, well, this picture is illustrating, mostly because it's what I remember, the Coulombic force. And it turns out your cross section is infinite for the Coulombic force. You have an infinite Coulombic, or cross section means that it's going to interact. Where if it's finite, it could miss. So in a practical sense, if we were thinking of billiard balls, that cross section would just be the cross sectional area of the scattering center. Units. What's the standard unit?
Barns.
Barns. And one barn is equal to
something to the minus 23?
24.
Oh, 24.
Square centimeters. Okay, so that's my my cross section. Then we have the omega is a solid angle. It's scattered through. So if you make a complete sphere, the solid angle is 4 pi steradians. The units are steradians. By the way, this is actually not the SI unit. This is what the textbook said. If you want to get it to the SI unit, you have to go to meters. I should have thought, because there's 100 centimeters squared. Okay, so sigma or omega is the solid angle the particle scattered through. So here you have a particle coming through d sigma, scattered through d omega, and that scattering, differential scattering cross section is this, which is the important thing we can measure to tell us about scattering. That's saying, it comes through some area here, it's likely to scatter through some area here, or some solid angle. And remember I said, just think of the solid angle like the area of a sphere with radius 1. So you just take the equation for area of a sphere, which is 4 pi r squared. Put in 1 for the radius, not units, just 1. And that gives you. You had an epiphany there?
I'm still annoyed about that.
Sorry. And finally...
I'm not annoyed about it. I'm contemplating it, I should say.
Trying to figure out what the next step is to do and how it's going to affect you. And
well, next step is just let it ride and see what happens. But, yeah, let things cool over, get my head on straight, and then see what happens.
the center of scattering center. We call this a scattering center. So the center of it is not the scattering center. The entire thing is the scattering center. So the impact parameter, how close a particle would come to the center of the scattering center if no interaction. That's one way of describing it.
Oh, get partial credit.
And the units are, I'm just going to put in meters. We didn't talk about the units, but it's units of length, and that's the SI unit.
Yeah.
So there's our first question. And of course, it's going to be the biggest part of the credit because it had 3 things you had to describe, and you had to describe multiple ways. Okay, the next one, how does the lifetime of the particle relate to its decay constant?
I remember the equation, so I wrote down some words.
Oh no. That I thought was free points.
Yeah, I wrote down that equation too.
Did you?
Yeah.
Good. It's also right here.
Yeah, well...
But you couldn't see that when you were doing it. I mean, you shouldn't have been able to see that when you were doing it.
No. I think I wrote that down.
Now, what is this lifetime?
It's, well, the decay constant is the probability of decay.
Right. Probability of decay for each second.
Yeah.
Or each unit of time.
Yeah, well, I didn't clarify that, but yeah, probability of decay. Yeah. And then lifetime is, well, the average of how long it's going to be there.
Okay, it's the expectation value for life. Because
The
some will be very short, some will
yeah.
be very long.
Yeah,
and this is the expectation value.
Expectation based off of the average, which is why where we get the decay constant is the average.
Well,
right?
the decay constant is, I mean, clearly it's a probability because it's a probability. Yeah. It's kind of redundant to say it's a probability, but it's a probability that exists because of the nature of the particles. That's why we had Fermi's golden rule. What's the function of Fermi's golden rule? It allows us to find the decay constant and the differential scattering cross-section. Right, the reason we're doing all of this stuff with the toy theory is to understand how we can get a theoretical equation to find this decay constant, and from that to find the lifetime. Or how we can get that differential scattering cross-section in theory. Okay, any questions about the quiz?
I don't think so.
You said no?
Don't think so.
It's our second quiz. We're on a roll. And it's going to raise your grade.
Yeah, it should. Wasn't there one day you were late to class?
I don't think to class.
The lab's been a little iffy. But yeah, whatever. I think there was one day.
The first day of lab, I was late getting over here.
Yeah.
After that, I think I've been pretty darn prompt.
Yeah, well, we just adjusted a little bit. Yeah. Because, yeah, I thought there was one day, and we should have a quiz that day. One that I made.
Speaking of which, you still have one lab period to make up, don't you?
Yes, I do.
Okay.
Just waiting for a lab that, do.
Here we have the rules for toy theory. I've rewritten them in a different fashion so we can see the factors more clearly identified with their steps. And obviously I've gone through toy theory again to make sure I've got this straight. And what we're going to do is go through the examples in the textbook and make sure that we understand how to do this toy theory and how to combine it into Fermi's Golden Rule. So just quickly reading over this, and I have this printed out so I can refer to this as we go through our examples. We're going to do the examples 631 and 632. And then try to go back and see if we can't do the example that I tried to do before. So step 1 was label incoming and outgoing for momentum with arrows. So you're labeling all of the for momentum with arrows. Then for each vertex, you put this factor. For each internal line, you put this factor. For each vertex, so in other words, for each of these, you have one of these. And then for each internal line, that's not one that's external, but one that's internal, you have one of these factors, and then you integrate over internal momenta, and finally you cancel the remaining delta function. This here is going to remove all but one of your delta functions. You're left with one delta function. That's the one that gets replaced with its 2 pi to the 4th power by I. So we have those rules, and we're going to apply them, because seeing the rules, applying the rules, two completely different games. Anybody can see them. So we're going to start with the decay of A. So what we have is, here's A. Here's B, and here's C. So A is going to decay into B and C. And so now I apply my rules. So applying rule 1, I have label all my momenta. So I'm going to have, here is momentum A, here is momentum B, and here is, whoops, I put B with C. That was a stroke of genius. Here's a beautiful pen. It's almost out of ink as well. That'll work, okay.
I was hoping, I don't have a black pen. All I have is 3 blue pens.
This one's black.
Because sometimes multiple colors come in handy.
Okay, so I labeled all my momenta here. Now we go to step 2. Write a factor of IG for the one vertex. On your picture, indicate where the vertex is. I just want to make sure that we're, okay. Just want to make sure that we're speaking the same language. Is that one dying? It really is just about out of ink.
Yeah, I'm curious how much is actually...
Darn it. Sorry.
Whatever.
Well, this one's black.
You want to toss me a red one? Oh, fancy. We got everything lined up here. Yeah, I'd toss that one.
I think so. Okay, so my first thing to do for toy theory is I'm going to, whoa, went off on its own. I'm going to, for step 2, write down my just 1 minus IG. Just 1 because I only have one vertex. So that was rule 2. Now I go to rule 3. Rule 3 said for each internal line, write a factor of, well, there's no internal lines. Right, internal There's nothing.
Yeah.
It's just the incoming and the outgoing. So I skip right by rule 3. Rule 4, write a factor of 2 pi to the 4th power d, and then the k's are the momenta. And you pay attention to the direction of the arrows to decide if it's positive or negative. So at my one vertex, the one coming in is positive. So which one's coming in at my first vertex?
A.
So I'm going to have PA. The other two are leaving, so minus PB minus PC. And that's D to the... Nope, that's not... Yeah, that should be D to the 4th. Pretty sure it should be D to the 4th. Okay, check the book. You got the book open. I know I didn't write D to the 4th in my equations, but I think it is.
What are we looking
Because these are 4...
Right here?
Yes. It's, yeah
rule, D to the 4.
Rule 4. Well, the rules are listed here, rule 4. Yeah, D to the 4th. Okay, so I've got a typo in my rules. I'm going to go back and fix that on this. At least when I got to doing it, I saw the typo. I'm getting better at identifying my mistakes compared to the test I gave yesterday. Okay, so I write that down for my one vertex. I've got my signs there. There are no internal momenta, so I don't need to put in any factors for those and integrate them out. Right? This has both put them in and then integrate them out. And so I go on to step 6, which is integrate out the 2 pi to the 4th, delta to the 4th. Replacing with I. So what that is I'm doing an integral over the external momenta, PA, PB, PC, and when I do that integral, this entire thing here is just going to become I. And so what I'm left with is minus IG times I, or minus I squared G, or just G. I squared is minus 1.
Oh, this I is imaginary.
Yeah.
Okay.
Now this G is important. Do you remember what G is?
Gravity.
It's the coupling strength. So this is on the order of G. I could have had other variations on this. I could have, for instance, had something like we did before, where it goes, here's a B, here's a C, becomes an A again. That added 2 additional vertices, right?
Mm-hmm.
But for each vertex, you write a factor of minus IG, so that would have been G cubed for its order, instead of G for its order. I'm going to undo this.
Why is it on this that we do... Why does it matter that we follow this specific order? Or is that just...
The order is not important until you get down to the integral. So, for instance, you could have done this and this together at the same time. It to me would make more sense to put minus IG times 2 pi to the 4th times, the direct delta to the 4th, all in one step.
Yeah, because you put the vertexes together and then the internal lines together. Well, put that down there.
Yeah.
Oh. Well, so we don't know the reason why.
Yeah. I believe it was because he wanted to break it out by why you're doing them.
Okay.
And so they were for different reasons, and that's why he broke them out as different steps. So G is coupling strength. So this was on the order of G, since it's equal to G. Mm-hmm. And if I would have done the one that I showed here with the little loop, that would have been on the order of G cubed. And so the magnitude the one that's going to be the most important to us is going to be the one. Okay, now I'm saying this. I think it's true. The one that's most important to us is the one that's the lowest order in G. And so this is the one that we care about because it's the lowest order in G. So we have now M is equal to G.
What is M standing for?
M is the, what is it? I can't remember what its name is, but it goes into our equations in Fermi's golden rule. It's telling us about the geometric probability of a decay occurring. So what are we going to do with this? I mean, we successfully did what is obviously the simplest case possible for using these rules. How are we going to make any use of that whatsoever? I mean, it would be a waste of our time if we don't have a reason or a function for it.
I thought that's what physics was. Physics is, it's not because of physics that we have that computer sitting right there. Those two have nothing to do with each other.
We're going to use this to find the probability of decay. If we can find that decay constant, then we can find its lifetime, right? Since the lifetime is one of decay constant.
Sense.
And so from our previous work with Fermi's golden rule, we had gotten to this equation.
Is that supposed to be script M there?
Yeah.
Yeah. Okay.
Yeah, remember when we first introduced it, I said I can't find this character on the computer, so I'm just using an M.
Yeah.
So this is like equation 6.35. So for a single particle decaying into two particles, this was the equation. So for our specific case, we had A decaying into B and C. Given that, what is S equal to?
Two? I don't know. What is this?
Remember, S was the number to keep us from double counting. If we have identical products, then we have S is equal to 1 over the number of identical products factorial. And if I have two different types of identical, then it's just going to be the product of what I'd have for each one. So how many identical products do I have in this?
0.
Okay, so S is just going to be 1. Right? If this had been B and B, then S would have been 1 over 2 factorial.
Okay.
So I have S is 1. P was my momentum final. Well, it's just going to stay my momentum final. M is G. Everything else is the same. So I'm going to have now I put the absolute value G squared. You don't need the absolute value at this point. And this is the same as it has. It's the bottom of the page, though, right?
Yeah.
Right, so it wasn't hard at all.
Yeah, they don't have the.
Oh,
G
instead of
squared on the
M1, it
outside.
should be MA.
Or
Yeah, they
whatever.
have it up here, but it's still the same thing. I just put it here so you would see, yes, that came from the M.
Yeah.
And actually, when I did this before, I put a 1 out here in parentheses to say S was 1. I didn't forget about it. It was 1. Okay, so that's the usefulness. We now have a way to determine what's going to happen in decay. So now we could take this and talk about, okay, I have a neutron. A neutron is unstable and decays. If it decays into just two things, say, thank you. Well, that would be three things. It can't decay into an electron and a proton. It has to be an electron, proton, and a gamma. But if it was just the electron and proton, then I could have used this for that decay. Okay, next case. 6.3.2, if we have two identical particles interact to produce a different set of identical particles. So the picture for this is A and A. Now, I cannot have A and A meet. You might wonder why I can't have A and A meet. Do you wonder?
A little bit.
Because when we started with this vertex thing before break, we said we're going to imagine a world where there are only three particles and they only interact like this. This is all you can make, a vertex with one A, one B, and one C. Now you can orient however you want, but that's all you can make.
But there's two A's and there's two B's in here.
Yeah, and you can't have two A's together, so I'm going to have something that separates them. And then I have a B that comes out and a B that comes out. So this vertex has an A and a B. What does this one have to be? It has to be C because I need A, B, C for each one. And so I can look at this and say right away if it's feasible or not, just because, well, is it possible for me to take these and make that up? Okay, then we do what I just saw you did. You labeled all the momenta, so you put, what do you call them?
The book is a P2 for that top one, but I hadn't labeled it yet. Do the book. And then P1 was down below. P4 and P3.
And then this one, you could go up or down. It's up to you.
It doesn't matter.
The book has it going up.
Yeah.
And that's going to be Q.
Because with stuff that we're doing on it, it doesn't matter which way it goes at all.
That's right. Well, because it's a virtual particle, it doesn't matter. It really doesn't matter. It's a virtual particle.
And why are we labeling it Q?
Because we're using Q for the virtual ones and we're using P for the actual ones.
How do we know it's virtual?
Because it's internal rather than external.
Okay, so we just assume anything internal is virtual.
Yeah. And so did they call this Q1 or Q5? Since you got the picture. He just called it Q. He said, let's not worry about labeling a number because there's only one. Yeah. So we have our figure there. My figure
matches the book.
Is not perfect. It's not perfect because it's hard to differentiate. Colors will help me differentiate. There, that's better. All right, so now we're able to do it. We've done step one. We labeled all momenta, 4 external and 1 internal. Now we write the factor of minus Ig for each of the two vertices. So just like before, go down here, minus Ig squared. Write a factor of I over Q squared minus M squared C squared for the one internal line. And that mass is this mass C, so I had to put M sub C for it. You with me?
Why are we using MC?
Because this particle here for the internal line was a C particle.
Oh, okay. So, okay, yeah.
Okay, the next step, write a factor of 2 pi the fourth, d the fourth, k1 plus k2 plus k3 for each of the vertices. So I have two vertices. Two pi to the fourth, delta to the fourth, and let's just do the top vertex first. What am I going to have for the top vertex? What's coming in?
It's going to be PA minus PB.
Well, for the top vertex.
Oh, because of C.
What's coming into that?
We're using A and C.
Well, no, we're using 1, 2, 3, 4, and Q. P1, 2,
Oh,
3, 4,
we're
and Q.
so it's 2 and Q.
Okay, so P2 plus Q.
Plus Q.
And what goes out?
Minus P4.
Right. So there's the first one. For the second one, I'm going to have another 2 pi to the 4th power, d to the 4th. Looking at the lower one, what's coming in?
P1.
And then going out is?
Q and P3.
Okay. Now we need to write a factor of 1 over 2 pi to the 4th power d to the 4th q for the one internal line. So I'm going to have 1 over 2 pi to the 4th d to the 4th q. There's only one q, so I don't put a subscript on it. Integral. And now I need to integrate. Now we didn't do the integrals before, right? Now we're going to do the integrals. So I look at this and I say, well, I have 2 delta functions. So let me just apply one delta. Now notice I have this delta here. Well, this 2 pi, dang it, I put the 4th power the wrong place. This here is going to cancel with one of these, right? I should have done that in a different color. And when you have colors, it makes sense to use them for different things so you can kind of keep track of the order of stuff.
Yeah.
So I did that canceling. Now I'm going to take this delta function. This delta function is 0 unless q is equal to P1, okay, move that across, minus P3. So I'm going to apply this one. So if I apply this one, my integral, I'm done. All I have to do is go through and everywhere Q appears, put in P1 minus P3, and I'm done with the integral. Right, so the integration is easy. And so this is going to equal minus IG squared I over, and instead of Q, I'm going to put P1 minus P3 quantity squared. Right, that was the first time Q appeared. And then, of course, I still have minus MC squared C squared. And then I have this first bracket. So I have the 2 pi to the 4th power, my delta to the 4th power of P2 plus, and for Q, what do I do with the Q? Same thing.
P1 minus P3 minus P4.
Okay, so now I have finished step 5 with doing the integral. You should feel a little accomplished now. Just, I mean, it wasn't a hard integral, but...
Do you have to worry about any of that other stuff, though?
Any of what other stuff?
D4Q?
That's the last step.
Okay.
Now we have step 6. Integrate out the 2 pi to the 4th with... There only should be one remaining delta when you get to step 6.
Wait, how do we get rid of the other delta exactly here? Because delta...
We just see, I have the integral sign here.
Yeah.
And so I applied this integral. The integral d4th q, so I was integrating over the 4 dimensions of q. And this delta to the 4th power is a delta function over the 4 dimensions of q. And so anytime you have integral some function of x delta x minus a dx, it doesn't matter what x is. anytime you have something like that, it's simply equal to, provided that A is within your limits, it's simply equal to f of A. Because of the way the delta function works. It's 0 everywhere except for when its argument is 0. Then it's 1. And so when you're doing this integral, you're going 0, 0, 0, 0, 0, 0. Oh, here I've got a value. 0, 0, 0, 0. Yeah. You add up everything and all you have is that one value.
Yeah.
And so that's what we physically did. That's what we did right here. We integrated over all of Q, but this delta meant that the integral was done if we just replaced Q with P1 minus P3.
So how did we get rid of that by the area right above the paint there exactly by how? Is that just how?
You're saying we got rid of this?
Yeah, I mean, I get how we canceled that, but how did we get rid of the second half of that? It's got, that
this part right here.
Yes.
That was the thing that was equal to 0 all places except when this was true.
Okay.
And so we got rid of that by putting Q equals P1 minus P3 everywhere it occurred, and getting rid of the integral sign. Okay. Right, so this was the thing that made it short. And it disappeared in the process of making it short.
Yeah.
Just like here, this right here, there is additional integration now over the P variable that he doesn't even mention. He just says you cancel it out. That means you integrate and it collapsed. And this here just becomes an I when you do the integral over that. So now I'm left with, okay, I got to erase this because I'm actually going to use this area. Now I'm left with minus IG squared times I times another I over P1 minus P3 quantity squared minus MC squared C squared. So,
the i's can go away.
You have I to the fourth power.
Yeah.
I to the fourth power is 1. So yes, they can go away. And so this just becomes minus G squared over P1 minus P3 Now, I think if you look in the textbook, they use the other delta function, and so they have a different function, I think. Yeah, they have P4 minus P2. We have P1 minus P3. The difference is clear, right? We just took the other incoming and the other outgoing because we applied it to the reason.
Oh, that Q is squared.
Yeah. The reason we're different is because they applied it to this one. They used this delta here. Yeah. We use this delta here.
I see that.
Based on the symmetry, you know that they have to be the same.
Yes.
So, this is equal to that factor m. So now we found m. What is it good for?
Finding its mass.
Oh, no. It's not minus, it's plus, because minus 1 squared turns out to be plus 1. Mm-hmm. Whoops.
I canceled my minus.
Good. I apparently forgot. Oh, my goodness.
You didn't realize it was this close?
I did not, and I have an appointment. I have to go.
All right.
Dang it! We're so close.
I know, that's why I was just
let me finish it, because we are so close.
Right.
We are so close. So, what do we do with this? Well, first of all, there is a second variation. This variation here. What's different about it? Nothing, except for P3 is on the top one and P4 is on the bottom one. That's the only difference. And so all you have to do is switch P3 and P4.
Yeah.
So you just change this P4 to a P3 and you get the other one. Or in our case, I wrote here the equations in the book instead of the one that we did. In our case, it would be change the P3 to a P4. And then you get your total. Because you have two of the same order, you have to take the total M as the two M's added together. And so you have your total M. Then we say, well, how is that useful? And they give us the simplest possibility. They say, let us suppose the particle A and particle B are the same thing, and particle C is a massless particle. That is, for instance, we had two electrons that sent a photon between them, right? That's what they're doing for their example. Mm-hmm. And in that case, then you can simplify the magnitude to just minus g squared over p squared sine squared theta. Oh. Where p is the incident momentum and theta is the deflection. And notice I'm on 9 of 10. You can combine that into this equation here. Notice final momentum over initial momentum. That's going to be 1, right? Because momentum is going to be conserved. Agreed? And the S now, because I had two identical particles, S is going to be 1 over 2 factorial, which is 1/2. Because you have two identical particles. E1 and E2 are going to be identical. And so this becomes just 2E quantity squared. And you put in your value for M that we got on the previous page and you're done. Here's my last slide. Higher order diagrams. This was only the 2-vertex option. You can make 8 4-vertex options of the same interaction, which would be annoying. But there is a very important one, the bubble diagram, where you have this that you can't solve. And it caused, according to the textbook, 2 decades delay in the advancing of this theory because no one could solve it. And finally they came up with a way to put a fudge factor in so that they could solve it. And they still end up with that fudge factor being a problem, but they say, that's unimportant. Look the other way, and we're able to get past it. And that does bring us to the end of the chapter.